Ladies and gentlemen, Blue Stool 28, Melanie Brown, what does a research mathematician have in common with a Champlain student?
Thank you. Thank you. So hello, for those of you I haven't met, my name's Melanie Brown and I'm in my third year as a math professor here. Before I begin, I want to thank the Blue Stool Organizing Committee for inviting me to speak to you today. I'm also tickled that this is Blue Stool number 28. Since mathematically speaking, 28 is what's called a perfect number. I only wish we had perfect weather for this talk. So if you add up the factors of 28, so 1, 2, 4, 7, and 14, what do you get? 28. That's the definition of a perfect number. 6 is also a perfect number, but Blue Stool number 6 was probably well before I got here. The next perfect number, 496, but I hope I don't have to wait that long to speak in the series again. I'm glad you all stopped by today. I was worried that with that M word in the title, math, that some people might be scared away. I'm going to be talking about math, but this is not a math talk. For that, I'd probably need some kind of chalkboard. Instead, we're going to be talking about connections. Math occupies a really interesting position here at Champlain. Some students, particularly in computer science and innovation and game programming, have a real natural affinity for math because they see the immediate relevance to their majors. Other students, though, might be viewing math as a necessary evil, or maybe even an obstacle to graduation. Why do these students feel that way? Perhaps they've never felt good at math. Perhaps they don't see the value to their major. And you know what? At different points in my life, I probably would have answered the question the exact same way. Math is a really broad subject. You know, when we think about science, we think about biology, chemistry, physics. Well, math has all of those same different areas. And when I was a grad student, part of what we learned was how to be conversant in all of those different areas of math. Confession. I really struggled with the area of real analysis. It did not come easily to me, and I did not feel like I was good at math while I was studying it. Looking back now, I can appreciate the value of it, but I still don't think I'm good at it. Now, while those of you at Champlain know me as a math professor, I actually live a double life. My secret identity is that of clarinetist and musician. I still play clarinet and actually have 2 concerts coming up in the next 2 weeks. I'm a creative person at heart, and I enjoy seeing how my creative side influences my more analytical side. When I started college, I actually wanted to be a middle school band director. I love music, so majoring in it seemed the natural choice. I also realized early on that I wanted to teach. I was initially drawn to middle school band because I thought it would be fantastic to get younger kids excited about instrumental music. I'd start them at the beginning before they could develop bad habits and inspire in them the same love that I have for the subject. And it wasn't until my senior year of college that I decided to transfer these same teaching goals to math. Now, don't get me wrong, I've always loved math, but in school, it was something I was good at, but nothing that I really had considered for a career. I thought different algebraic manipulations were fun. I love solving puzzles, so I loved solving for variables. Putting together geometry proofs was interesting. It was like connecting the dots between different facts. Doing derivatives in calculus was a blast. I liked analyzing each function to figure out which rules to apply. I enjoyed doing math for math's sake, but I didn't grasp at first why any of it was necessary. It wasn't until I got to physics as a high school junior that I started to view math skills as a toolbox that could help in different situations. As I started learning about projectile motion, suddenly the quadratic formula and the vertex of a parabola became really important. I was doing them for a real reason rather than just as part of a problem on math homework. Trig functions took on a new meaning as I started working with free body diagrams and forces and all of that. I wish I'd been able to make these kinds of connections when I took chemistry. It would have made stoichiometry and balancing chemical equations much easier. Being able to connect mathematical ideas in other contexts was immensely valuable for me, and it changed how I viewed the rest of my classes. Suddenly, linking verbs were equal signs, equating the subject with the predicate. Rules for conjugating German adjectives actually started feeling more like those derivative rules. Once I analyzed the basic structure and looked for certain properties, I knew what ending to put on. I carried this perspective shift with me as a music ed major. Music theory suddenly felt more like math. Or maybe math had actually just felt like music theory all along. If I needed to transpose something, I treated it like a graph translation. I also took music theory while I was studying number theory, so I started viewing scales in terms of modular arithmetic. Canon figures were another type of graph reflection. Retrograde reflect the Canon figure over the y-axis. Inversion reflect the Canon figure over the x-axis. Retrograde inversion reflect over both axes. In fact, as I kept learning more math, I kept thinking about how I could apply it to music theory. It all made me wonder, how might my educational experiences have been different had math been presented in a way that made me immediately recognize that toolbox aspect of math ideas? It also makes me more sympathetic to our students who view their math requirement almost like a box to check off for graduation. Math classes do not and should not feel like they live in a vacuum, separated off from other disciplines. Math is a language that helps us to understand the world around us and to make meaning from seemingly chaotic phenomena. A math class should provide students with the tools that arise from deep thinking, but the class should also help students to start to see how to connect those tools to different subjects. Professional mathematicians can also find themselves in a similar situation. As with any subject, deeper and deeper study leads to this laser focus in one niche area. And it can be easy to forget how your niche area relates to the broader realm of the discipline. I was awarded a Faculty Professional Development Fellowship this year to work on a research project that's an extension of my own dissertation research. I am what's called a topological graph theorist by training, which means I like to play connect the dots, not just on a piece of paper, but maybe on a donut or a trefoil knot or a Mobius band. In my dissertation, I was focused on this problem. Hold out your hands. In your hand, you have a bunch of dots, and each pair of dots is connected by a rubber band. Your goal is to stretch and twist that tangle of dots so that what you have, no matter how you spin it around, has a bunch of triangles and squares. Maybe not squares, maybe just general quadrilaterals. And we want the goal that every triangle only touches quadrilaterals, and every quadrilateral only touches triangles. So it's kind of like a checkerboard, just with different shapes there. So, framed this way, the problem is formally about embedding a complete graph on n vertices such that it has a regular bipartite dual. But I had taken enough math classes to know that there was another way to view the problem. Focus on the triangles and squares that result, and the problem jumps from topological graph theory to another area of math called combinatorial design theory. Because I had the tools from both areas, I could mix and match to come up with a solution. And it does turn out you can solve that tangle problem. You can do it whenever the number of dots in your hand is a power of 9. The more you know. After I graduated, my advisor did what many advisors do. Took my ideas and ran with them. Where I was viewing these as a big tangle that we stretch and twist, he saw these triangles and squares as an array. Label the squares across the top, put the triangles down the columns. Now to make my embeddings work, I put some labels on the vertices of these shapes. And I needed the labels to sum to 0. He took that same property with his arrays and made it so that the rows sum to 0 and the columns sum to 0. With a collaborator, he developed some constructions to generate more and more and more of these arrays with that property. He could start with a seed array and then use that construction to build arrays as big as he wanted. When he showed me these constructions, I started seeing more connections between what he was doing with these arrays in that array context versus what I was doing in my graph embedding context. My work is still in progress, but I hope to find the connections between the idea, because at its core, it's the same problem just being viewed through two different lenses. If these connections do indeed exist, then we've actually doubled the tools in our toolbox to solve these kinds of problems. When it's beneficial, we can use one kind of tool, but when it's also beneficial, we can use another kind of tool. And I'm actually attacking this problem with the same kind of tool I encourage my students to use, especially working out small examples just to get the lay of the land, the feel for what's going on. It's kind of like running science experiments to gather enough data to form a hypothesis. So I'm teaching Calc 2 this semester, and I see many of them here today. And as they know, a frequent refrain in class is to work smarter, not harder. By connecting different math ideas, we can actually let the math do the hard work for us. Now, for my students in Calc 2, that class is the first time where they start seeing valid reasons for wanting to, say, complete the square or use polynomial long division. All those algebra tricks they learned in high school have finally come home to roost in Calc 2. Unfortunately, when they were first encountering these, it was in that vacuum of Algebra 1 and 2. They were doing things just because they were told to do them, but they were never told why they'd want to do it or how it connected to anything else that they would ever want to do. I mean, why rationalize the denominator just cuts? Without these connections, my students didn't hold on to these tools. I'd like to hope that now they've got those connections, they can see how they can connect to other things and they'll hold on to them more. And they can see that that toolbox from Algebra 1 and 2 is still really useful. In fact, the hard part for most students taking anything in the calculus sequence is remembering and using all of those algebra tools. In Calc 2, we're also studying sequences and series. A sequence is a list of numbers, so you can already think that all those pattern recognition tools you had from when you were younger are going to be immensely helpful in recognizing the behavior of these sequences. We've also talked about the sequences themselves and how they can be tools. Numbers count things. Take the Fibonacci sequence, for example. That's one that a lot of us have met before. 1, 1, 2, 3, 5, 8, 13. It's pretty fun. You get to the next number by adding up the previous two. And the Fibonacci sequence shows up all over the place. As one example, mathematicians might like Fibonacci because those numbers count things. In particular, you can use Fibonacci numbers to count the number of ways you can arrange zeros and ones so that you never have two zeros together. Interesting. And in fact, the position of the number in the sequence tells you how many numbers you're allowed to string together, how many of those zeros and ones. The real fun is if we can find two objects that can be counted with the same sequence. Each object is connected to the same sequence, and then we can start looking for those connections directly between the two objects, eliminate the middleman, so to speak. This is a particularly exciting week for math at Champlain. 3 of our math minors will be presenting at the Hudson River Undergraduate Mathematics Conference. That's right, math minors speaking at a conference for math majors. For their talks, each student found a mathematical topic of interest, did some independent research into the topic, and will share what they learned. These students found really neat connections between math and their majors to highlight in their talks. I think it's why these minors are confident speaking at a math conference. Because of these strong connections, math doesn't feel like a totally separate part of their education. It complements the work they're doing in their majors. And really, that's how it should be for all Champlain students. What does a research mathematician have in common with Champlain students? Well, they should be looking for connections between mathematical ideas and other contexts. They should know that math provides all sorts of tools and a language for viewing the world, so long as you know to be on the lookout for these connections. The math connection problem is one that I can't solve by myself. I can help make you aware that these connections are out there. I've certainly seen plenty myself that I've highlighted, but I won't pretend to know all of the different connections. Our math minors presenting on Saturday knew that those connections were out there, so they took it upon themselves to find them. I encourage every student to seek out these connections. Your math professors will share the tools and demonstrate how to use them, but it's up to each of us to find the context for those tools that feels most relevant to us. I believe in the value of all students engaging in more abstract mathematical thinking. It's a great way to explore interesting ideas, and it's good practice exercising both the analytical and creative parts of our brain simultaneously. Mathematical thought is a much more creative endeavor than most people realize. I also believe that math ideas don't need to be applicable to be interesting. But I do see the value in helping students to understand how to connect these math ideas to their majors. I invite all of you, and I wish we had more of all of us, they missed the really good part. But I invite all of you to join me in a campus-wide conversation on how math and quantitative literacy do arise within our different majors. In particular, how do you see math ideas showing up in, say, our more creatively inclined majors? It's a great question worth investigating. As a musician, I know how math shows up in music, but I also know that we have many talented writers, communicators, and visual artists, and I want to hear from them. I want them to share the context where math ideas and math tools feel relevant. I want to then be able to highlight these connections in the classes I teach. I want them to help me, to help all of our students recognize that learning more math should complement what they're learning in their majors. I'm really excited to see where this conversation leads, and I thank you for the opportunity to share my ideas today.